Gautam is was one of the first students who actually joined our group, if you remember. In fact, when he joined for his master's actually, and there are two sort of really funny incidents about Gautam that I need to tell everybody. This is the last time I'll get a chance to do this. And so I had a discussion with Gautam and Shiva in my office. And so I told Gautam, I think you should do a PhD. And he said, I'll have to ask my parents first. So, and when he said that, I had a good laugh. And, and right after he said that, right, Shiva also said, yeah, I also have to ask my parents, right? So I don't know whether they really asked them or not, but in any case, right? So then sometime during the middle of his PhD, Gautam decided that he needed to change fields. And he said, look, the work that I'm doing here is very, very applied and engineering oriented. And, I really want to become a professor. And so I said, okay, so what do you think a professor's life is? Well, my vision of a professor is you put your legs on the table and you think. Remember that?
Yeah.
Okay. So I said, okay. And, he went and tried some other stuff. And after a couple of weeks, not a couple of weeks, a month, he came back and said, hey, I think I want to go back and continue the work I was doing or do something more applied. So I think Gautam has gotten quite a lot of experience over the last few years. He's done some really amazing work actually here at UCLA, and obviously we're very sorry to see him go, but he has to. Okay, we have so Gautam, I wish you all the best, and I want you to why don't you start your defense presentation now?
All right.
Okay.
All right. Thank you so much, Professor. So hello, everyone. Thank you for the committee members for being here for my defense. So the title of my talk is a flexible heterogeneously integrated micro-LED displays in elastomeric substrates using fan-out vapor packaging. So here's an outline of my presentation. So first I'll go over the introduction and motivation of the talk about the process flow that we use for making these flexible micro-LED displays. I'll then go over some of the experimental work that we have done with respect to micro-LED mass transfer using the technique of adhesive bonding, the demonstration of a flexible micro-LED display on the FlexJet platform, and finally, I'll summarize the work and provide future work.
Just pause at the appropriate points to ask a question.
Yes. Okay. So first, let's move on to the introduction and motivation section. So if you see the slide, micro-LEDs are essentially the ultimate display technology. And if you see this particular table, it basically compares different display technologies that are commercially available versus the micro-LEDs. So what we typically observe is that micro-LEDs can provide far superior brightness as compared to these other display technologies, with a brightness exceeding about 1 million candelabras per square meter, which is 3 orders of magnitude better than the next best, which is the plasma display. These micro-LEDs are made of inorganic compound semiconductor materials such as gallium nitride or indium phosphide. And because of the crystalline nature of these materials, the electron mobility is very high. And because of this, these devices can be shown to have very fast response times in the nanosecond range. And also because of the fact that they're inorganic, these inorganic crystals, they also can be operated at much higher currents and for a very long duration of time. In fact,
you want to be on that side and I'll operate the thing.
Yeah. Oh, so Kyle told me it's more, you can hear better here.
Oh, okay.
Yeah, that's why. So in terms of lifetime, they can exceed more than 100,000 hours. Micro-LEDs have been shown to have power efficiencies, especially UV micro-LEDs, power efficiencies more than 60%. So because of all these advantages of micro-LEDs, there's been a push both in industry as well as in academia to try to make displays using micro-LEDs. There is also a particular need for flexible
one question, Goutham, on the speed. Can you explain why plasma and OLED and others are very, very slow? I mean, 10 milliseconds is a very, very long time. Why is that?
Yeah. So in the case of things like LCDs, like you essentially have the liquid crystal layer, which basically controls the polarization of the light. So those have a much larger inertia when they are electrically activated compared to something like micro LEDs. And OLEDs, because they are organic crystal, they're an organic material. Also, the electron mobilities are much worse compared to the micro LEDs. And materials such as gallium nitride and indium phosphide are known to have very high electron mobilities because of their band structures. So that's why they have several orders of magnitude better response times compared to those other display technologies.
So the ones that are based on just the gallium, which one is the gallium nitride? Is that the micro LED you're talking about?
So actually, I did micro eyelid. So it's called micro LED, but some people also refer to it as micro eyelid. So the eye is inorganic. So it's basically an inorganic 3-5 semiconductor based light emitting.
Right. That makes okay. Thanks.
So there is also a particular need for these displays to be flexible. So you need flexible micro LED displays. And that essentially comes in certain specific application spaces. For example, in defense applications, you need conformable vehicular displays for efficient solid state lighting. You also need flexible and smart wearable displays for in-field combatants, especially those displays like you can see in the image on the right, which has to be worn around, for example, the arm, but also be clearly visible in ambient lighting conditions, for which you need displays that can provide a very high brightness, which only micro LEDs can fill that gap. Then there are also emerging applications such as, especially in medicine, where there's a new field called optogenetics, where light is used to stimulate cells like neurons in order to study them and also in order for therapeutic reasons. And optogenetics is, for optogenetic stimulation, you need light sources that can provide a very high power density, which can be done only using lasers or using micro LEDs. The displays for these kind of applications also has to be flexible, because of the fact that they have to be implanted within an animal or within the body of within the human body, or sometimes even conform to a curvilinear surface within the body. For example, on the image on the right, you see a micro LED display used as a cochlear implant for doing the optogenetic stimulation. The third application is the commercial sector, and in the commercial sector, the need for micro LEDs is mainly in wearable displays for augmented reality, virtual reality. Because in this particular application space, again, you need a display that can have a very high refresh rate because of the data rates of current video, and also you need essentially a display that is very bright, so you can even see the images when you are in ambient lighting conditions. There's also a need for flexible micro LED displays for automobile head-up displays. So what all these three application spaces have in common is that you need a display that is very bright, can work in ambient lighting conditions, and can conform to any curvilinear surface. Okay. So, yeah. However, there are several challenges that are basically present for fabricating these flexible micro LED displays. So micro LEDs, as I mentioned earlier, are based on inorganic 3-5 semiconductors like gallium nitride, indium phosphide, that cannot be directly fabricated on flexible organic substrates because of their high processing temperatures as well as lattice matching considerations. So the way that they are usually to be integrated on the flexible substrate is to first fabricate them on a separate growth substrate, and then they are then to be detached from this growth substrate and then massively parallelly picked up and then assembled onto a target flexible substrate using a process called mass transfer, which I'll discuss more in detail in the coming slides. However, here is where the problem lies, because micro LED mass transfer that is currently done in both industry and literature is mostly done using techniques such as viscoelastic stamps, like using a PDMS stamp to stick to and pick up the LED using van der Waals adhesion. And these kind of mass transfer techniques are typically very complex and also have poor yield. They are also not compatible with high quality GaN micro LEDs, which are grown on sapphire substrates, because these kind of LEDs have to go through a process called laser liftoff to detach them from the growth substrate, which these kind of mass transfer approaches cannot really handle because the forces that hold the devices are weak. The other set of issues in making these kind of displays has been that current flexible electronic approaches themselves do not naturally support heterogeneous integration. this is because they are typically based either on using printing techniques or some kind of evaporated metallization, where the metal pitches are typically coarse, and also the different components such as microcontrollers, driver ICs, and so on that is needed for a fully working display are typically assembled using flip chip bonding with some kind of solder, which limits the achievable interconnect pitches as well as the pad pitches. They also use thin film metallization or printed interconnects, which have a very high series resistance that can lead to large voltage drops while driving large arrays of micro LEDs. So any questions? Okay.
So for so I just had one question, maybe on the medical application you mentioned. Seems very exciting. Can you comment on the biocompatibility of micro LED? To what extent this needs to be kind of interface with a tissue or something that requires like stringent biocompatibility requirement?
Yes. So yeah, that's a good question. So the gallium nitride is a very stable crystalline material. It's generally non-toxic. So when blue LEDs are blue or UV LEDs are used to stimulate the cells, the way optogenetics is done is you genetically modify the animal in such a way that certain ion channels become light sensitive. But you can control what frequency of light actually opens or closes that particular ion channel. So if blue LEDs are used using gallium nitride, it's typically safe because the material is very stable and biocompatible. But there are some ion channels which have to be controlled using a red wavelength of light, which is done using indium phosphide, which is an extremely toxic material. So in those cases, more work has to be done to try to encapsulate the package so that the intercellular fluid never touches the LED or doesn't contaminate something.
Makes sense. Thank you.
And do that with things like Parylene and so on.
Yes, yes, yeah. In our process, yeah, we have a way to package the devices as well.
Perfect.
So, yes. Yeah. So in this chart, I basically provided some samples of what people have done in this particular field. So on the left side, this is an example from literature where this group had actually sort of printed 200 by 200 micron square LEDs on a PET substrate and then interconnected them using thin film evaporated metallization. And on the right side here, this is an example from industry in a company called Excellic Print that uses viscoelastic stamping technique to actually pick up and then assemble the LEDs on a PET substrate, where they have interconnected them either by using evaporation or by using electroplated interconnects. So now, because of the various issues that I mentioned earlier, in this work, we have essentially come up with two innovations that actually helps us to overcome the issues. The first one is that we have come up with a novel mass transfer approach that uses adhesive bonding and has a much simpler implementation and potentially higher yield and scalability. And our mass transfer approach is also compatible with gallium nitride laser liftoff, which is used to release GaN micro LEDs on sapphire. So if you see the figures in the bottom, so the left side summarizes the conventional mass transfer approaches. If you can see the table, it either uses an electromagnetic technique by using either an electrostatic or a magnetic stamp to induce electromagnetic forces to pick up the devices from a carrier, or it uses a viscoelastic stamping technique wherein a PDMS stamp is essentially used and the devices are picked up using van der Waals stiction. So these conventional approaches, the transfer stamp itself is very complex, as you can clearly see, because in the electromagnetic case, the stamp needs electronics on it and special drive circuits to control the amount of electromagnetic field produced. And also in the viscoelastic case, the forces that hold the micro LEDs are typically weak. So during the transfer process of these devices or the printing process, some of the LEDs could actually detach or could shift in their position, causing yield issues. It is also extremely sensitive to the planarity of the overall sample. However, in our approach, which is shown on the right side, we essentially use adhesive bonding and laser debonding in order to do the mass transfer. So here what we do is we use a lithographically patterned glass stamp with a coated adhesive, which we bond to the device we want to pick up. And then we use a laser debonding to release the device and transfer it to the stamp. And finally, we can do a laser debond step to release it from the stamp to a target. In our approach, so I'll talk more in detail about how this approach is done, but this is just an overview of the fact that in our approach, the transfer stamp is very simple because it's just a lithographically patterned glass substrate. The forces that hold the micro-LEDs are also very strong because it's a strong adhesive bond. By controlling the thickness of the adhesive we can also control the sensitivity of the process to the planarity of the sample. So any questions? The second innovation is our flexible electronic integration approach, which we call as FlexTrade, which is a die-first fan-out wafer-level packaging process that allows us to heterogeneously integrate vastly different components, such as the micron-sized devices with millimeter-sized dielects, all together in a common reconstituted substrate at very fine interconnect pitches of less than 40 micron. So if you see the schematics in the bottom, you can see on the left side that would be a conventional flexible electronic approach of trying to make a micro-LED display, wherein the devices would first be printed face up on, for example, a flexible substrate like PET. Then the RDL will be fabricated on top of that. And finally, the ICs that have to be integrated would be flip chip bonded on top of this flexible substrate. However, in our approach, all the components, including the micro-LEDs as well as the dielects, would first be placed on a certain wafer, and then the molding compound, the final substrate material will actually be compression molded on top of our devices, so that all the devices will be embedded in this molding compound, and then we can directly interconnect the various components using back-end of line metallization. So in our approach, we do not use any solder. We directly metallize on the pads, and so we can bring the devices much close to each other and attain much higher integration densities. And we also by avoiding the use of solder, we can also integrate components that have a much finer pad pitches. So any questions?
I have one question, but I don't know if you want to answer it later, but how compatible is this process with the existing, like a PCB manufacturing techniques? I want to see, like, once you guys establish this, how much modification is needed from the industry side to be able to accommodate this?
Yeah, that's actually a very good question. So actually, that's one of the selling points of our approach. Because these approaches that you see on the left side, they actually require very specialized equipment to do. For example, the electrolysis stamp from LuxView, which is basically acquired by Apple. So they have built a specialized tool that does the stamping process.
No, I think the question is a little different. I think what the answer I think he's looking for is how are you going to put this on a PCB? Okay. Now, you don't need to put this on a PCB. This is the PCB. So that's the.
Sorry. Is that?
No, but I'm asking that. Yes, this would be our PCB, but can we use the existing infrastructure, let's say pick and place kind of tools that they have, all those things adapted for this kind of substrate?
Yeah. So
explain it in detail.
Yeah. So should I explain later?
Yeah.
So the mass transfer process is more universal. So we can use this technique to assemble devices on any substrate. So we could assemble it on like a silicon backplane or even a PCB backplane. Because in the adhesive bonding approach, the only processes that are involved is die to wafer or wafer to wafer bonding and laser debonding, and those techniques are already available in most packaging centers.
You are going to go through the book.
Yes, yeah. So let me now move on to.
Actually, Goutham, this is Shiwa Wang. I have a quick question on the slide. The good thing about the left side is that you can pack the micro LEDs in good aero density because the die 1 and die 2 is at the back of it. But in your approach, actually, if you're looking at the light emission at the back, the aero density has some alternates that die 1 and die 2, right? So are you confident that this is really what they need?
Yeah, so you're right. That would be a disadvantage here because the light has to first pass through the PDMS before coming out. but we can typically thin the dyes to like maybe around 50 microns or less than 100 microns. So the PDMS is a very low loss material for most of the light wavelengths that we talk about here. So the light would not attenuate that much when it comes out to the PDMS.
Mhm. Right. I meant the aerial density, because the left one you can pack, let's say 1024 micro LEDs together, whereas there is no dead space, right? Because the die 1 and die 2s are at the back of it, at the top of it. Whereas your architecture on the right, you have die 1 and die 2s, which will limit the packing density if I'm looking from the backside.
Yeah. Oh, you're talking about like because here they are more 3D stacked as compared to here. Because
That's right,
everything
3D stack, right? Because we, for example, for AR and VR, we really want as many pixels as possible in a tight density.
Yes, that is true. So yes, that would be a disadvantage in this approach because all these components are present in the same area. But in the future work, I have shown some of the work we're trying to do to 3D stack our flex rate itself, so that we would, for example, put the dyes on one flex rate, which would be the backplane layer, and then the micro LEDs on a different layer, and then we would basically 3D stack them by using alignment, so that the LEDs will be very high density, but they'll be sitting on top of the driver plane.
Okay, yeah, thank you.
So one quick question. So between this palmite and PDMS, which one has better thermal conductivity? And also, can you comment on the transmissivity of these two materials for infrared for like 1.5 micron and 1.3 micron?
Oh, okay. So from my knowledge, I'm not sure. So you're asking PDMS versus PET?
No, the first question is which one has better thermal conductivity?
Oh, I mean, they're both pretty bad. I would say that PET would be slightly better compared to PDMS.
So like practically what would be the reasonable maximum power consumption or heat generation that you can tolerate on these LEDs?
So typically these LEDs have to be driven to around 1 milliwatt per square centimeter, right? Optical brightness.
Like no, in terms of like how much they're going to generate heat when you turn on, like how much heat you can dissipate.
Unfortunately, I don't have like the numbers in the top of my head as to what exactly those values would be. But I don't have an idea about what I mean, I have like a rough idea of what the thermal conductivities of these are, but I don't know exactly what the amount of heat flux which is produced.
Yeah, but I think the point that Professor Bawakani is talking about is if you had to heat sink this, okay, the surface of the LEDs is available for heat sinking in this particular product, right?
Yes.
But as far as we know, there is no need to do that yet.
Yes, you're right. Yeah. Also, there is one additional thing is that in the conventional approach, they usually use thin film metal or sort of printed interconnects, which have a poor thermal conductivity than in our case, where we use thick electroplated interconnects. So the interconnect layer here itself would act as a heat spreader to try to extract the heat from the LEDs and spread it out. But high power operation of these devices, especially very high brightness operation, would be an issue in both cases because the substrates are very poor thermal conductivity.
Do you think you can use VCSEL diodes? Because we're using these VCSEL laser diodes that are really small in terms of size. I mean, you can potentially integrate those as well. Do you think that can be also compatible with this approach? These are laser diodes.
Yes. We can integrate laser diodes too using this mass transfer approach.
I think we should go to
Yeah, I'll talk about the process. So now let me talk about the process flow. So essentially, there were two approaches of fabricating these flexible, heterogeneously integrated micro LED displays that we explored. The first one is the so-called mass transfer approach, which essentially involves 4 steps. The first one is the release of the micro LEDs from the growth substrate to a temporary carrier. Then the selective adhesive bonding of a glass stamp, followed by selective transfer of the bonded micro LEDs from the temporary carrier to the stamp. And then finally, transfer of the LEDs from the stamp to the target, followed by performing fan-out wafer level packaging for heterogeneous integration. So this is a schematic of what that would look like. So the leftmost is essentially you have these prefabricated LEDs sitting on a certain growth substrate, onto which you bond this temporary carrier and then do a process called laser liftoff that essentially releases the device's face down onto this temporary carrier. And then you use a glass stamp with adhesive on it, which you align and bond, and then pick up the devices, which is shown in the middle step, and then finally transfer them to the target substrate. The glass stamp can then be taken, cleaned, and then reused again in the next cycle of printing. So this is how a typical mass transfer process or approach would look like. The second approach that we explored is a dielet approach, where what we do is we thin down the growth substrate with the micro LEDs to less than 200 micron thickness, and then we dice them to less than 1 millimeter square dielets, and then we pick and place these dielets with the micro LEDs directly onto a target substrate, and then perform fan-out wafer level packaging for heterogeneous integration. So I'll talk about the advantages and disadvantages of each one of these approaches, and also talk about the details of how they can be implemented to make our flexible micro LED display on FlexRay. So so now I'll go over the detailed process flow. So in the mass transfer approach, so first we have these prefabricated micro LEDs on a certain growth or sapphire substrate, where there's a thin layer of UGAN which is present between the devices, so they are not yet completely singulated with respect to each other. And these are commercially obtained wafers. In the second step, what we do is we essentially deposit or electroplate a 5 to 10 micron thick layer of nickel on top of these devices, which I'll talk about. The reason for this I'll talk about later. It is to actually act as a stress buffer during the laser liftoff process for releasing these devices. And we use the same nickel to also dry etch the UGAN between the devices so that they are now completely singulated. Next, in step 3, you can see that these singulated devices on the sapphire is then bonded to a temporary glass carrier with the HT3007 adhesive, which is a thermoplastic polyimide which we use for this adhesive bonding process. And then we perform a laser liftoff step, which essentially detaches these LEDs from the sapphire substrate and then completely transfers them onto the temporary glass carrier. Next, in step 5, we do some basic cleaning on the surface and also essentially dry etch the adhesive between the devices so that the adhesive is also now patterned. And then we can do our mass transfer step on this particular sample, wherein we have these LEDs sitting on the temporary carrier face down, and we bond to it a glass stamp with adhesive on it to selectively bond to those LEDs we want to pick up. And then we do a programmable laser debonding with an eczema laser to the backside of the temporary glass carrier, so as to detach only those LEDs that we essentially want to transfer to the stamp, which is what you see here. And then once the LEDs are sitting on the stamp, we can then clean the surface and also wet etch or remove the nickel layer on top, so that we have these LEDs with the contacts exposed sitting face up on the stamp, on top of which we can do some testing before assembly on FlexRay. So this is basically the mass transfer process for basically taking the LEDs from the sapphire and then placing it on the stamp. So any questions?
Goutham, just a quick question. So in step 4, I assume it's a floodlight kind of illumination. So would that affect the HT3007 adhesive? You see, have this purple layer on top, right? Some of it would actually affect that. So would that affect your yield?
Yes, it would ablate the surface, so it would cause some ashing at the surface. But what we do is after these devices are released, we actually dry etch the adhesive using photoplasma, so that the adhesive, the damaged area of the adhesive between is removed.
I see. That's a good idea. Yeah, thank you.
It has a very small penetration depth, so it doesn't damage the adhesive too much.
Makes sense. Yeah, thank you. Yeah.
So yeah. So next we move on to do the FlexRay process. In the FlexRay process, we essentially have, as shown in step 9, a FlexRay carrier, which could be a silicon or a glass wafer, on top of which we laminate a thermally releasable adhesive tape, which has a release temperature of around 110 C. We then flip chip place these LEDs on the stamp onto this, and then we do a final laser debond step with an eczema laser to transfer the devices completely onto this thermal tape. And once all the LEDs have been fully assembled on the tape, we can then flip chip bond other components such as a CMOS driver die or a driver IC or a microcontroller. And then we do our fan-out process. So in step 12, we dispense the PDMS, and then in step 13, we compression mold the PDMS on these components using a second flex rate carrier with its own thermal release tape having a higher release temperature. We then thermally debond the first carrier so that we get this flat surface with the components embedded in the PDMS. And then we can do our RDL metallization using back-end line processing to define the two levels of interconnects needed to connect these components. And after the interconnects are made, we completely debond the bottom carrier. So that is what you see in step 15. So after the metallization, as well as the thermal debond of the carrier. So now we have this essentially this flexible PDMS substrate with the embedded CMOS dies along with the micro LEDs. And the LEDs emit through the PDMS and the light emission is essentially through the backside. So any questions?
I have one. In terms of the materials choice, how much flexibility do we have when it comes to PDMS? I know that it serves as like an elastomer, but is there something inherently unique about PDMS that we cannot use any other type of elastomer to do the job for us? Or would you envision when we translate this into industry, still the substrate would be kind of PDMS in nature?
Yeah, so any elastomeric, I mean, this particular process is a standard like fan-out process. So essentially any kind of molding compound could be used. But we would prefer to use an elastomeric material such as PDMS or a silicone, which is silicone. The reason being that there is an issue called die shift that happens during the compression molding process of the molding compound over the devices. So what happens is when you compression mold the molding compound, it actually exerts drag forces on the devices, causing them to shift in position. And so you need to, and that actually limits your achievable interconnect pitches and so on. So the reason why we use PDMS in this is because PDMS has a low Young's modulus, and also the drag forces produced during the curing process is very less. And we can also cure it at room temperature because it has a below room temperature glass transition temperature.
The other reason is we do PDMS for other projects.
Yeah, right. And it's also very transparent to this, to most of the wavelengths of visible light. So that's also another reason.
Thank you.
Yeah. So next, let's see how the dielet approach is done. So in the dielet approach, we take a standard thickness sapphire wafer, which is around 500 to 700 microns thick, with singulated micro LEDs on them. And then what we do is we thin down the sapphire substrate to less than 200 microns thickness, and then we dice the substrate into less than 1 millimeter square sapphire dielets with micro LEDs on them. And then once we have in step 3 this individual sapphire dielet, we can then do pick and place for assembly onto the flex strip. So now this is a repetition of the flex strip process. So we have the tape, and then we flip chip place this sapphire dielet with the LEDs. But this time the sapphire is not detached from the devices, and it exists as part of the final substrate. So we have the sapphire dielet, and then we can then place the other components as well, then do the dispensing of PDMS, compression molding, metallization, and final thermal debond. So in this case, we would get a display that is not as flexible as the mass transfer case, because this still has a rigid sapphire dielet, but it would still be flexible because of a so-called bicycle chain concept, wherein like you would still have the sapphire dielets separated by PDMS between the dielets, and that would make the system reasonably flexible. But in this kind of approach, the light has to first pass through the sapphire and then to the PDMS, and then it comes out from the backside.
You may want to mention why this approach was used, because of the transferring the wafers to Japan and back. And
yeah, I'll talk about that like in the, yeah. So now I'll talk about the advantages and disadvantages of each approach. So here you see the comparison between the mass transfer approach as well as the dielet approach in terms of the different attributes. So in terms of the process complexity, the mass transfer approach is more complex because it involves two adhesive bonding steps and 3 laser debond steps. And so it is a more expensive process, and also takes a much longer lead times for using this process. In the case of the direct approach, the only extra steps is wafer thinning as well as dicing, and hence it is much simpler. In terms of the process throughput, the mass transfer approach can get very high throughputs because we can simply increase the size of the stamps that we use for doing the process. In the case of the direct approach, however, it is typically low throughput because it is really limited by the dialect size. So we use 1 millimeter square dialets, and we cannot essentially use smaller dialets because it will be more difficult to handle. And if you use larger dialets, it essentially compromises on the flexibility of the overall sample. Then this is very important in terms of the micro LED structure dependence. What we found is that the mass transfer approach does not work with conventional LED structures because the contacts can actually delaminate while doing this process, and we essentially need to make special LEDs with customized structures with stress buffer layers so that the contacts are well preserved. Then, however, in the case of the direct approach, it's completely independent of the micro LED structure that we use. In terms of resolution or the PPI of the display, the mass transfer approach is really limited by the amount of adhesive reflow that we get during the stamping process, as well as the thermal expansions during the bonding. A PPI of up to 500 we discovered was possible, but anything more than that was very difficult due to the reflow of the adhesive. In the case of the direct approach, each individual sapphire dialect can have any PPI because it's really defined lithographically. But then because the dialects have to be separated by a certain interdialect spacing to account for flexibility, PPI greater than 300 would be difficult in this case. Then finally, in terms of flexibility, the mass transfer approach, because the LEDs are essentially present on the surface of the PDMS, a very thin surface of the PDMS, the flexibility is really limited by the flexibility of the metallization itself, and up to 1 millimeter bending radius is possible. However, in the case of the direct approach, because the flexibility comes from the bicycle chain concept, it is limited by the die spacing. So from ANSYS simulations, we found that for a 1 millimeter square dielet with 300 micron spacing, which is what we typically use, up to about 5 millimeter bending radius is possible without damaging the.
I think Goutham, you missed one very important disadvantage of the dielet approach, and that is if you were trying to make a multicolor approach, a multicolor display, the dielet approach doesn't work. You need some other things. While in the mass transfer approach, a multicolor thing is definitely possible.
Yeah, because you can transfer 3 colors of it.
Yes.
Yes.
That is a big disadvantage of this.
Yes. Yes. Any questions?
One maybe question I have is regarding the limited flexibility of the metallization you mentioned for the mass transfer approach. What kind of strain profile were you expecting? Like, is this 1 millimeter good or bad, this radius of bending, or?
So the flex strength that we typically make, for example, for this particular case, is 500 microns thick. And so 1 millimeter bending radius, 1 millimeter bending would be almost equivalent to folding the sample. So, so in our particular test setup, we essentially 1 millimeter is like the minimum bending we can essentially do without breaking the wires. So the breaking of the wires, the stress profile is just because the wires, the PDMS is an elastomer, so it can actually stretch. But when we try to bend the wires too much, then the stretching of the underlying PDMS kind of cracks the.
Yeah, but that's a fatigue issue.
Yeah, it's a fatigue issue, right?
Yeah.
So there's a. Yes.
Yeah.
Because I was gonna say that seems like this metal wire is gonna get cracked, right? Once they're under deformation, right? And I'm thinking, to what extent would it impact the performance of micro LEDs? Because obviously, even if there's no crack, and let's say that we don't have total device failure, but we do have increase in resistance, is that tolerable? And based on your experience.
Actually, I have not included that as part of this, but my colleague Arsalan has actually done a lot of studies on the reliability of copper interconnects on flex straight. So what his analysis showed is that, one thing is also we don't directly metallize on the PDMS. We usually have some stress buffer layers. And also the interconnects are usually corrugated. So they are vertically corrugated. And that's to reduce the buckling that is present on the wires. So So his analysis showed that when you initially start bending the wires, there are some micro cracks develop, but then the micro cracks sort of release some of the stress and then it sort of saturates. So then what happens is as you continue bending it, the degradation in the series resistance of the wire is only up to about 5%. So beyond that, the resistance of the wire sort of settles out. So so you can expect to get around 5% degradation in the wire series resistance during bending. So his experiments, he bent up to 6,000 bending cycles.
I see. Thank you.
Yeah. So now let me move on to the experimental section of showing micro-LED mass transfer using adhesive bonding. So here in slide 51, you can essentially see the on the left side optical image, you can see the image of the prefabricated micro-LEDs on the sapphire substrate that we essentially obtained from a commercial manufacturer. And here you also see me probing the device and the VI characteristic. On the right side is after performing the first steps of trying to electroplating the nickel stress buffer layer on the device, and also dry etching or singulating of the device by etching the UGAN between the devices to expose the sapphire. So once this has been done, the next step, of course, would be to bond these singulated devices to the temporary carrier, which is what can be seen in this slide, where basically we have done in two scales. So we have done it in die scale or in wafer scale. So in die scale, what we do is we essentially dice the sapphire wafer into a bunch of 10 millimeter by 12 millimeter pieces, which is then bonded to the temporary glass coupon with the HD adhesive. In the wafer scale, an entire wafer of the LEDs is bonded to another wafer of glass with the adhesive. So because of some tool limitations, because a wafer-to-wafer bonder was actually down for around 2 years, so we had to shift to the die scale so that we could do this using a die-to-wafer bonder. So essentially in this work, the process is essentially done or demonstrated at the die scale. So now once the sapphire, essentially the sapphire with the singulated devices is bonded to the temporary carrier, the next step is to perform the gallium nitride laser lift-off process for detaching the LEDs from the sapphire substrate onto the temporary carrier. Before I continue with this particular process, I will talk more in detail about some of the work we have done to improve the yield of the gallium nitride LLO process that is needed to release the LEDs from the sapphire. So before that, any questions? Okay. So now let me talk about some of the work we have done with high yield gallium nitride micro-LED laser lift-off. So this chart summarizes how the GaN LLO process actually happens. So this is a typical cross section which shows the sapphire substrate in the bottom, which is polished in the backside. And then you have the GaN micro-LED stack and then the glass carrier at the very top. So a high power ultraviolet excimer or a Q-switched IR laser, third harmonic, is shown from the backside of the sapphire substrate. And it passes through the sapphire without much attenuation because of the large band gap of sapphire. But when it hits the interface of the GaN and sapphire, it is actually absorbed within about tens of nanometers. The absorbed light is converted to heat and the temperatures can rapidly rise to more than 900 degrees Celsius. And when this happens, the gallium nitride actually dissociates into liquid gallium and nitrogen gas in a process called as ablation. And this process is a very, very high stress process because there is this released nitrogen pressure, which is created because of the gas absorbing the heat. And there's also a significant transient thermal gradients at the interface, which also induce significant stresses on the films. So a combination of both of these mechanical stresses can often cause cracking to the GaN films. And in this work, what we have done is we have tried to model the LLO process itself and tried to come up with an engineered stress buffer, which we put on top of the LEDs so as to improve the yield of the LLO to almost about 100%. The image on the right basically shows the typical setup that we use for doing this GaN LLO process, which is done in DISCO in Japan. So essentially, a solid-state laser is used, which is Q-switch, and the third harmonic, which is 355 nanometer, is basically shined on the sapphire substrate using a galvo control. and it creates beams, Gaussian spots on the surface, which is then sort of raster scanned using this control system. So any questions about the process? Okay. So now let's talk about some of the work we have done to model the LLO process itself to understand the various stresses, mechanical stresses that occur in the GAN film. So for doing this modeling, we essentially assumed an axisymmetric model. So the geometry is essentially cylindrical, and you have essentially the sapphire at the bottom, the GAN, and then this nickel layer on top of the GAN, and then finally the glass. We assume, so the laser is basically shown from the backside of the sapphire substrate. And in our particular experiments, we use a 355 nanometer light wavelength, where the incident dose of the light was around 600 millijoules per square centimeter. Because the incident light was essentially from a solid state laser, its intensity profile, temporal intensity profile is also Gaussian, given by that expression, with a pulse width of about 10 nanoseconds, and the peak of the pulse occurring at 25 nanoseconds from time t0 equals 0. There are also some assumptions here, which is that the diameter of the GAN film is around 25 microns for the simulation, and the thickness of the GAN is 7 microns. And even though we use a Gaussian beam spot on the sample, for a first order approximation, we assume that the lateral intensity of the light is essentially uniform. So there is no lateral variation in the light intensity. Any questions about the assumptions here?
I think Goutham, let's move on a little faster. It's coming up to an hour.
Oh, okay. Okay. Yeah. So yeah, sorry. So now what we can do is we can essentially use this information to get the transient intensity variation in the GAN thin film as the incident light pulse strikes the interface, and that is given by this expression, which takes into account the transmittances at the two interfaces, the exponential decay of the light intensity within the GAN thin film, and also the temporal dependence. And once we have this transient light intensity variation within the film, by taking its gradient along the z direction, we can essentially get the heat generation rate, which can then be substituted within the heat transfer equation to solve for the temperature transients at the interface. So here is an ANSYS simulation of the temperature transients when the light pulse actually hits. So when the light pulse hits, we see that the temperature at the interface rises to around 1800 Celsius and then falls rapidly as the heat is essentially conducted away. So here I've plotted what the average temperature averaged within the beta GAN inverse region, which is essentially the penetration depth of the light within the GAN film looks like. You can see how the temperature rises rapidly to around 1800 C when the light hits, and then the temperature falls down as the heat is conducted out. So now that we have the information about how the temperature rises when the laser pulse hits, we need to somehow get the mechanical stress information from this temperature transient information. There are two sources of mechanical stresses that are present during this process. One is a thermomechanical shock wave that is essentially created due to the large transient temperature gradients at the interface. And there's also a pressure shock wave, which is created due to the released nitrogen gas absorbing the heat and then rapidly expanding at the interface. So the thermomechanical shock wave can be directly simulated in FEM by directly using the interfacial temperature information. But however, for extracting the interfacial nitrogen gas pressure information from the transient temperature information, further simplification of the model is basically done. So, so in this slide, slide 61, you can essentially see how that simplification was done. So again, I've replicated the cross section here. We essentially assume that all the GAN within the penetration depth of the light is completely decomposed into liquid gallium and nitrogen gas. We can make two observations here. One is that the diameter of the GAN thin film is much greater compared to the region of the GAN that has actually been ablated. And also at this particular temperature and within the timescales of interest, which is a few pulse widths in tens of nanosecond range, the diffusion length of the nitrogen gas is also much smaller compared to the diameter of the GaN thin film. So under these observations, we can approximate that within the time scales of interest, which is a few tens of nanoseconds, the nitrogen gas within this ablated region can be assumed to be bounded or trapped at this region. So for a trapped gas, we can essentially describe it using an equation of state. So this particular gas I have now described using an ideal gas equation of state, as you can see here. And using this ideal gas equation, I can essentially extract what the pressure of the nitrogen is directly from the temperature transient information that was calculated earlier. The number of moles of gas is just the total gas that was decomposed within this 1 hour beta GaN region that was ablated. So here you see a plot of the pressure of the nitrogen pressure as a function of time in nanoseconds. And you can see how when the incident light pulse hits, the pressure rises to around 400 megapascals and then starts falling off as the heat is conducted away, which we have approximated by a Gaussian pressure pulse for using in our full ANSYS simulations. Any questions? So here you see the results, the full results of the ANSYS mechanical simulations of the GaN LLO process, which takes into account both the thermomechanical shock wave as well as the nitrogen pressure shock wave. So on the left animations, it basically plots the normal stresses in the cross section, and on the right, it essentially plots the normal deformation multiplied by a factor of 10. The key points here is that what we observe is that during this process, when we don't use any nickel layer, the peak stress in the GaN is around 1 gigapascals. But when we use a 10 micron thick nickel layer, the peak stress essentially falls to by an order of around 5x to around 0.2 to 0.3 megapascals. If you see the animation in the bottom right, which is a normal deformation when the nickel is used, you can clearly see how this process actually works. So when the incident pressure pulse actually hits, the pressure shock wave hits, the nickel actually plastically deforms and acts as a cushion for the incoming shock wave, which in turn reduces the peak stress within the GaN because the stress wave is essentially dissipated in the nickel itself. And this is the reason why the peak stress within the GaN is significantly reduced when we use this nickel stress buffer layer. So if you see on the right side graph, that's a plot of the peak stress within the GaN thin film plotted as a function of time for 3 different cases when no nickel is used, when a 5 micron thick nickel layer is used, and a 10 micron nickel is used. And you can again see how the peak compressive stress falls rapidly once we increase the thickness of the nickel from 0 to 5 and then to 10 microns. So this is essentially, this modeling shows how the nickel layer would help in preventing stresses in the GaN film, thereby improving the yield of the LLO process. Any questions?
I'm curious, actually, what boundary conditions did you use for the top side of the gallium nitride?
So the top side of the gallium nitride is where the pressure shock wave, the pressure pulse is actually applied. So that entire area is applied, is basically supplied with the constant pressure or force, which was calculated using the simplification. The bottom of the glass carrier is assumed to be fixed.
I see. And then did you try to use continuity kind of conditions? See how would that be different instead of fixing the glass carrier? Or are you thinking that the thickness is actually resembling the?
You asked. So you're asking like the thickness of the glass below?
Yes. If it's thin, I see that fixing it could maybe make sense.
So it was assumed, so I've shown a zoomed in. So the glass carrier was assumed to be around 700 microns thick, and the bottom of that was fixed.
I see.
Yeah. So to confirm the results of this analysis or the insights from this analysis, we also did experiments. So here you see a 25 by 25 micron square micro LED after performing LLO with and without the nickel. So on the left side is with the nickel layer, a 10 micron nickel, where you see that the films have been released without any cracking. But under the same process conditions, when we don't use any nickel layer, you see that nearly 50% of the devices have cracked significantly. And this was also confirmed more using PL measurements, which also showed that when we don't use nickel, the PL intensity falls by around 2x order of magnitude compared to virgin devices on sapphire. But when the 10 micron nickel is used, the PL intensity is essentially comparable. So this also confirms the results of the modeling that we had done earlier. Yeah. So now let me continue with the micro LED mass transfer using adhesive bonding. So I'll quickly move through this. So these are just experimental results. So this is, so once the sample were bonded, we performed the LLO process. So now you see the micro LEDs sitting face down on the temporary glass carrier with almost 100% LLO yield. Next, we actually do our mass transfer using the glass stamping process, where you can see here the top SEM images show a fabricated glass stamp with the pattern adhesive on them. So the left side is a normal pattern where every LED is picked up, and the right side is a checkerboard pattern. The adhesive is also lithographically patterned on these glass mesas, so as to control the amount of reflow that the adhesive has during the bonding process. The optical images on the bottom essentially show the samples looking through the glass stamp after bonding it to the LEDs sitting on the temporary carrier. So on the left side, you see the normal pattern where every LED has been bonded to, and on the right side is a checkerboard pattern of LEDs that have essentially been bonded to. So once this bonding is done, next we do the selective laser debonding using the excimer laser to completely transfer the devices from the temporary carrier onto the glass stamp. And that is what you see in this slide. These are the LEDs now fully released from the temporary carrier and sitting face up on the glass stamp, but still with the nickel stress buffer on top. So this is a normal pattern on the left and the checker pattern of LED on the right. Next, we wet etch this nickel layer so as to expose the contacts. And here you see the devices sitting on the glass stamp after the nickel has been removed, where we are essentially probing the devices. The VI characteristics on the right side essentially show a comparison of the forward VI characteristics between devices on the stamp versus micro LEDs which were on sapphire. And what we observe is that at a forward operating voltage, less than 5% degradation in the forward current was observed. However, we did face a problem while doing this mass transfer process, which is that if you can notice, the contacts in many of these locations had actually delaminated once we removed the nickel. And what we found later was that this was actually due to a micro LED manufacturing issue rather than a process issue itself. So I'll talk about this in the remaining slides of this presentation. So anyway, we decided to go ahead with the process to show that we can assemble these micro LEDs on PDMS. So here you see this is the placement of the stamp on the thermal release tape, where the LEDs have now been, if you see the center blackish region, so those are the micro LEDs sitting face down on the thermal release tape after the final laser debond step. We have also flip chip bonded some silicon dielects that you can see there to demonstrate heterogeneous integration. So next we dispense the PDMS and compression mold the PDMS. And here you see some SEM images of the same sample after the first handler has been thermally debonded. So on the left side, you see the normal pattern of the LEDs which are embedded on the surface of the PDMS. The middle is the checker pattern, and the right side is a silicon dielet embedded within the PDMS. So these kind of bubble-like features that you see on the surface is actually an artifact of thermal release tape, because the thermal release tape, if you notice here, has some roughness. And when we compression mold the PDMS actually fills those holes, and those are the roughness that you see here. Next, once these LEDs are now embedded in the PDMS, we essentially debond the second handler. So here you see the sample after the full thermal debonding of the second handler with this flexible PDMS, which has around 10,000 micro LEDs embedded in it at 300 ppi resolution. And here you see me bending it to less than 5 millimeter bending radius without any damage to the devices. So at the moment, for this particular sample, the metallization has not been defined because of the contact delamination issue. So any questions? Okay, now I'll move on to the demonstration of a functional flexible micro LED display on FlexTrade. So although we had demonstrated the successful mass transfer to assemble the GaN micro LEDs on FlexTrade, the micro LEDs were purchased from a commercial LED manufacturer which uses a conventional LED process. And what we found is that the way a conventional LED process is meant is it's meant to essentially dice up the device without removing the GaN from the sapphire and then packaging it in epoxy. So this conventional LED process is not actually compatible with device singulation, LLO, or transfer printing, which is typically used in mass transfer, as the contacts could easily delaminate during these processes because of the high stresses involved. So you can see in the figure in the bottom, the images in the bottom that shows that before the singulation, you see how the contacts on the devices are intact. But after we start singulating these devices, you notice how the contacts begin to delaminate. So for making micro LED displays with mass transfer, we need to essentially build custom devices, taking into account the stresses that are involved during the mass transfer. And this will be discussed in the future work section. But however, for a functional display demonstration, we decided to go ahead and use the commercial LED samples we had in hand by using a direct approach to demonstrate the flexible display. For most display applications, a PPI less than, for wearable displays, a PPI less than 300 and a flexibility of around 10 millimeter would be sufficient. So we decided to go ahead with using this direct approach to demonstrate the flexible display. So this slide shows the design. So the design, so this is actually a GDS file of the design. So the central square region has around a 10 cross 10 array of sapphire dialects. Each sapphire dielet has 135 micro LEDs, of which 40 of them are interconnected as part of the passive matrix. The dielets are 1 millimeter square, and the entire display is 80 cross 48. The display has two levels of metallization. The horizontal lines essentially short the P contacts and connect to a series of voltage driver ICs, which is present at the bottom of the design. And you have also the vertical lines, which short the end contacts of the micro LEDs in a column and connect to the series of current driver ICs, which are present at the top periphery of the display area. We also use a 15 kilo ohm resistor dielet, which is used to set the value of current for the current driver IC. So here are more details about the driver ICs that we integrated as part of this display. So the left side is a voltage IC. So I won't go too much into details about this, but it's a high power voltage driver IC. And the right side is a current sync IC, which is used to sync the required current through the micro LED. The amount of current that needs to be synced by this IC can be set by a current set resistor. And so we use a 15 kilo ohm resistor to set this particular sync current to around 3 milliamps. These devices were also not available in bare die form. They were actually obtained from they were actually extracted from PDF packages. So here you see an animation of me testing the ICs after the bare dies after extraction from the package, where they have been wire bonded to a chip carrier and then used to test a test display before assembly on FlexRay. Now here you see the fully fabricated micro LED display using the dielet approach, which has all the sapphire dielets as well as the display driver ICs integrated. And on the right side here, you see the display after fully releasing it from the FlexRay carrier, where it has been conformed to a 10 millimeter bending surface. In this chart, I've shown further zoomed in images of the various components that have been integrated as part of this display. So you see the left side is a current driver IC, the MAX 6971. The middle is the MIG 5891 voltage IC, and the right side is the resistor dielet. So these components have very fine pad pitches, and we essentially had to use two levels of metallization to essentially interconnect or integrate these devices as part of the display. Here you see a further zoomed in image of an individual sapphire dielet that has around 135 micro LEDs, of which 40 micro LEDs were essentially connected as part of the passive matrix. The reason why I used 40 micro LEDs was to limit the number of display driver ICs we needed to use for this demonstration, and also to simplify the metallization process. If you further zoom into the metal layers, you can see how the two metal lines has been fabricated. So the horizontal lines which short the P contacts essentially connect to the voltage IC, and then the vertical interconnects which connect to the current IC. The way the two lines have been fabricated is that in all those regions where the metal lines don't overlap, they lie on the same level of flex rate, But however, where the two interconnects essentially crisscross or meet, there is a 5-micron thick bridge of SU8, which separates them to prevent them from shorting. The reason why we decided to make the display using this approach was that by patterning this dielectric, which is made of SU8, which is a stiff material, we can improve the flexibility of the overall sample. Any questions about the fabrication? Okay. So here you see a video, you see a video of the display operating in scan mode, where the micro LEDs are essentially being driven by the display driver ICs. This sample, the way that the control signals as well as the data for the ICs were provided was through a probe station, through an Arduino setup. The display brightness was measured using a luminance meter to be around 10 power 5 candelas per square meter, which is around 1,000 times of that of a similar OLED display. These samples, however, because we use the commercial LEDs, micro LEDs, they could not be singulated. So because of the contact delamination issue, hence all the LEDs in a row essentially light up, and we were able to show this display only in a row scan operation because of this thin UGAN between the devices that tends to short adjacent devices. But since this is just for a demonstration purpose to show that we can heterogeneously integrate micro LEDs with the driver ICs, this would be a very good prototype for that. So this chart shows a comparison between the display that was fabricated in this work versus other similar flexible displays in literature. So in terms of the minimum micro LED pitch as well as wire pitch that we can achieve, we are good because of the FlexRate integration approach. We can also demonstrate a PPI between around 150 to 300. And this is also the only work where silicon CMOS driver ICs were integrated on a flexible substrate as part of the display. However, more work has to be done in integrating much smaller LEDs because in the future we wish to integrate less than 50 cross 50 micron square devices and also build larger displays to more than 100 cross 100 arrays. So any questions?
Yeah, I just want to say it's very impressive, actually, what you have done so far. I read through your thesis very carefully. Very nicely done.
Thank you. Yeah, so now should I go in the future? Okay, so now I'll quickly move on to future work. So the first one is to, the first future work is to try to make FlexState micro LED displays using custom micro LEDs. So as I mentioned earlier, the micro LEDs that we have in hand from the commercial manufacturer had this delamination issue. So in the future, we wish to fabricate micro LEDs in-house by modeling the stresses that are involved during the mass transfer process, and hence build the LED in such a way using engineered stress buffer layers to make sure that the contacts could not delaminate during the process. So here, I'll quickly show some preliminary work that was done in this direction. So you see here on the left side, a conventional process where the LED is first defined and then the contacts are essentially evaporated on top. The middle, you see the new mass transfer safe micro LED process, where after the contacts have been fabricated, a stress buffer, which is using a combination of silicon oxide and silicon nitride, is essentially deposited and patterned so that some of it overlaps with the contact area, which in turn helps to reduce the stresses within the contacts and prevent them from delaminating. So on the right side here, you see the optical image of the fabricated LED that we did at UCLA, where the dielectric overlaps with some region of the contacts, which helps to prevent the contact from delaminating. And on the right side, you see the SEM image of the device after singulation, where the contacts are preserved. So we plan to use these kind of in-house fabricated devices for in combination with the mass transfer approach to build flexible displays in the future. Should I go through this?
Goutham, I have a quick question on slide 92. Yeah. So some of the micro LED sizes are smaller, 10 microns, 8 microns or so. So do you foresee that your approach would be this, and this protective stress buffer layer is very impressive. Do you think it would also work for 10x smaller LEDs, micro LEDs?
Yeah, no, that's a good question. So for this, we designed using this particular size because so very small LEDs we really can't integrate at the moment on FlexRate because of our metal interconnect pitches that we can achieve. But in those cases, I think we need to specifically model for those sizes to find out how the stress buffer thicknesses would scale down to that size. Yeah.
Okay.
The stresses would be I would say, much worse once we go to much smaller LED sizes. So like it's going to be more critical to preserve the contacts.
The contacts, yeah. Okay, thank you.
So I think I'll skip over this.
Skip this.
Yeah.
Just go to your power.
Yeah. The full.
Yeah. You can go to this.
Yeah.
You say this is work going on.
Yeah. So this is some of the future work that's actually going on with right now, which is so till now I've talked about how to make a single color micro LED display, but for a commercial product we need to show full color display with the integration of essentially to have RGB colors per pixel. So there are two ways to making this. One is to transfer print each color of micro LED separately using 3 separate mass transfer steps, or to have one color of micro LED and then use a color conversion layer such as phosphors or quantum dots to generate the other colors. So approach 1 using the 3 mass transfer steps is expensive because mass transfers are usually expensive and also typically a low yield process, and hence compounding them can significantly reduce the overall yield. Approach 2 using phosphors is also difficult because when the micro LEDs shrink down to tens of micron size, there's significant non-uniformity issues because the phosphors themselves have particles that are in the tens of micron size. So approach 2 using quantum dots is the most practical for this display technology because of its small size, uniformity, as well as the high color saturation that quantum dots can achieve. So, quickly, the advantages of colloidal quantum dots is that they have narrow emission line widths, they can have high quantum yields, and most importantly, quantum dots can be dispensed using inkjet or aerosol jet printing for integrating them on the display. So here I show a quick illustration of a process flow that we are currently working on to try to integrate quantum dots with a display backplane so as to generate full color displays. So again, we would start with some kind of carrier with a thermal tape on which we would pattern essentially some resist patterns to prevent optical crosstalk. And then we would sequentially dispense using aerosol jet printing a red, green, and then a blue quantum dot to generate this quantum dot matrix that you see on the right side top image. And then once this quantum dot matrix is defined, we can essentially spin coat an adhesive on it, such as PDMS. And then what we can do is we can take this color conversion layer and we can essentially 3D stack it with alignment on top of a flex straight fabricated micro LED display, which is what the majority of this talk was about. But here the micro LEDs would be UV LEDs because they would be more efficient and they can essentially excite the quantum dots to generate the 3 colors. So once these are aligned and 3D stacked and we release the carriers, we essentially get this optical pump plane of micro LEDs, which will generate UV light that will excite and create the 3 colors for a full color display. Yeah.
So what the power?
Power was before this. Should I talk about that? Yeah. So quickly, I'll talk about the other. Another thing is that so there are some application spaces where the form factors are typically very constrained, such as in the case of contact lens AR or optogenetics, where apart from the fact that we integrate all these components at high density, we also need to take into account how we can transfer power as well as data, which is most readily done by using an RF technique. So we had also done some preliminary work here to try to build some toy prototypes to show that we can do wireless power transfer on a flex straight platform. So here you see a fabricated wireless power transfer system on the left side optical image with a secondary coil and power management ICs. Essentially here, this uses a 2-coil resonant magnetic coupling to transmit power. We plan to essentially use this kind of a power transfer system to wirelessly send power and data to a micro LED display.
Another thing.
Yeah, right, and other components of it. So to summarize, here's a summary of my contributions in this research. So I developed and experimentally demonstrated a novel micro LED mass transfer and assembly process using adhesive bonding which was used to assemble 50 by 100 micron square devices, LEDs on elastomeric substrates at 300 ppi resolution. I had also developed a very novel approach for high-yield gallium nitride laser lift-off using an engineered metallic stress buffer layer. And the use of stress buffer layer in improving this LLO yield was also experimentally verified in a DPSS LLO process. I had formulated an empirical model to study the ablation stresses during the GaN LLO process, wherein a simplified analytic model along with FEM analysis was used to confirm the efficacy of the nickel stress buffer layer to prevent the cracking of these devices during LLO. I had also demonstrated a prototype flexible micro LED display using the FlexRate platform, wherein a dielet approach was used to heterogeneously integrate commercial GaN micro LEDs at around 150 ppi resolution with off-the-shelf display driver ICs on a common PDMS substrate. Flexibility of about 5 millimeter bending was shown for this display. So here's a summary of some of the references and patents that were made in this research. And I would like to express my sincere gratitude to my advisor, Professor Iyer, for his invaluable guidance, support, and useful discussions. I would like to thank Professor Chiwe, Professor Sam, and Professor Iden for being on my defense committee and for their valuable suggestions and guidance. I would also like to express my gratitude to Dr. Ajit Paranjpe from Vico Instruments for his guidance and support with the project. I'd like to thank Frank Way and Jay Lee from Disco for their help with the GaN LLO process. I thank all our sponsors at CHIPS, including Semiflex Tech, ARL, SRC, and the UCLA CHIPS Consortium. I also thank all my colleagues at CHIPS for their helpful discussions and camaraderie. And I thank UCLA, NRL, and ISNC research facilities and staff for their support. Thank you for your attention.